kind of scattering, say, against electrons, and if they're rapidly exchanging energy per Hubble time, then that's kinetic equilibrium. Chemical equilibrium means rapid number changing, which, for example, would be here I'm calling pi dark matter. I'm going to often call it pi dark matter. Maybe anti-dark matter. And here time is left to right for me. So here I have pi electron with pi electron, here I have pi bar. So so chemical equilibrium is when you can rapidly change number densities. Whereas you see this one, you have the same state beginning and the end. You haven't changed number density, you can only exchange energy. But here you change number densities. Okay, so those are the two types of equilibrium. Okay. Now, we'll be interested in the number and energy densities of things like dark matter. And these are given just by an integral over the phase distribution. Okay, so piece of momentum. This is the number of degrees of freedom of the particle. So if it's a scalar, if it's 1, etc. Blah blah blah. Okay, and energy density will also be given by an integral over the phase space distribution, but now multiplied by energy. Here, the energy dispersion will be the usual thing. Okay. Yeah.
Here, I have a question.
Please.
What about thermal equilibrium? So both these kind of different equilibria are encompassed in the thermal equilibrium, or what about?
Yeah, I think when people, honestly, I've used that word and I don't know what it means. I think when people say thermal equilibrium, they often mean both kinetic and chemical.
I mean, thermal equilibrium means just that you can define at any kind of state at any time a temperature. But
well, yeah, this is gonna define a temperature. So maybe if that's what you mean, then that's synonymous with kinetic equilibrium. I'm gonna say a little more, but yeah.
I mean, what you described here are just processes, and you say about the rate at which these processes happen.
Yeah.
Defines somehow an equilibrium.
Yes, and I'm gonna maybe hold the question. I'm gonna say a little more about what this means in a second, and then ask me again. Okay. Yeah, and you can also define a pressure, which will also be some or an integral over the phase space distribution. This time, a different function ends up appearing here. But yeah, so number density, energy density, pressure are all just integrals over phase space distribution multiplied by the correct thing. Okay, so now let me state in terms of these objects what these equilibria mean, and then maybe that'll help. So kinetic equilibrium, when you have rapid energy transfer, it will set the phase space distributions to the equilibrium distributions that you're familiar with. So kinetic equilibrium implies that the phase space distribution is the following. Over temperature, so -1, where minus is boson plus is fermion. In the classical limit, where you can neglect this, it's the Maxwell-Boltzmann. Otherwise, it's the whatever Planck Fermi-Dirac distribution. So by kinetic equilibrium, if you have rapid energy transfer, then these Fs will take this form, where it depends on the energy, the chemical potential, and the temperature. Yeah, sorry. So is that what you would call thermal equilibrium when this is true?
Yeah, well, so this would be a special case if you have bosons or fermions and you assume you have thermal equilibrium. Then yes, but I guess this one means that chemical equilibrium is not.
Well, yeah, I haven't. Yeah, this is so. If mu is allowed to be arbitrary, then I haven't yet specified anything about chemical. And this is just kinetic equilibrium. Okay. So chemical equilibrium is going to imply relationships amongst chemical potentials of the different states. And if you have an interaction that's faster than Hubble, it will equate the sum of the chemical potentials of the initial and final states of the interaction. And it always goes both ways. So, for example, if it's a 2-to-2 process, where I just label the states I, J, K, L, and time is moving left to right, then it would imply, that mu I plus mu J is equal to mu L plus mu. I want to decay. Okay, you can do the same for decays or 2 to 3, whatever. And each reaction will imply one relation, and then in general, you have to consider every reaction that's occurring, and that'll give a whole system of equations that'll have to be solved simultaneously. Often, if you have a bunch of reactions, they'll just set everything to 0. The only solution will be all the chemical potentials are 0, but not always, and you need to be careful. And in general, you need to consider every interaction that's present. So let me do a quick example to show you how the chemical potential of dark matter can be set to 0 by annihilations.
Sorry.
Yeah.
Again, let me say again, this was the first point for me. It would be very interesting to know that. When one says you are in the departure of chemical equilibrium, not chemical but thermal equilibrium. So you are going into non-equilibrium case. Does it automatically mean that you are not in kinetic and also not in chemical equilibrium? I still don't know what thermal equilibrium means. Sorry. I'm just defining for you kinetic equilibrium and chemical equilibrium. Because this is often stated in some papers. They always write, okay, you are in a non-equilibrium.
Yeah, I think they mean one of these two. I'm defining kinetic equilibrium, chemical equilibrium. Kinetic equilibrium is rapid energy transfer. It ensures that the phase-space distributions take this form. Chemical equilibrium implies relationships amongst chemical potentials.
Yeah, but this always to me, you always assume that you are in a grand canonical ensemble.
Oh, sure.
So, and therefore, this means in order to define such an ensemble, you are in thermal equilibrium, right? You must understand that. Because otherwise, you cannot define the temperature. Like you have in your equation there, you have the denominator, you have the exponential function of temperature. This always assumes that you are in thermal equilibrium, because otherwise, you cannot define such a temperature, right?
Sure. Yeah, in my language, that is kinetic equilibrium implies that there's a temperature, and if you depart from kinetic equilibrium, then there is no longer a notion of temperature in general. And then your phase-space distribution could be some arbitrary function.
Yeah, because this is often misleading in some references or papers. They talk about thermal equilibrium, but yeah, definitely more. Yeah, one has to be more specific about that.
Yeah, I'm not sure.
Quite often different.
So when you say thermal, I'm not sure if it's synonymous with these two or a subset, or if it's a third thing. So maybe we can talk more after. But I'm only defining these two: kinetic, chemical.
Yeah, sorry for it.
No, it's good to be careful. Okay. So let's do an example. Suppose that dark matter, well, here I'll take it to be its own antiparticle. Suppose it rapidly annihilates into electrons and positrons. And then we can also consider two standard model processes. Let's see, so electron and positron can rapidly annihilate into photons. Well, I guess I can actually draw Feynman there. And I'm going to actually need a third one. In the early universe, there will be photon number changing processes that are also rapid. For example, I can take electron and send it. This would be called double Compton scattering, where you have a different number of photons in the initial or final state, and it could go both ways. Okay. Now, if all three of these are rapid compared to Hubble expansion, then what can we learn? And here, so here, 2 mu pi is equal to mu electron plus mu positron. Here, electron plus positron is 2 photon. And here, mu electron plus mu electron plus 2 photon. Okay. So what does this third one tell me about the photon's chemical potential? 0, thank you, because I can just subtract off sort of this from this side, and then I get mu gamma equals 0, because this is just changing the number of photons. Okay, and then I can sort of go back to here. This is 0, so then these sum to 0. And then that's the right-hand side here. So now I conclude that the dark matter has 0 chemical potential. You see, I needed all 3 interactions to conclude that, and actually just a subset of 2 of them wouldn't have been enough. Okay. So often, if you have a bunch of interactions, you'll just set all of them mu to 0, but not always. And be careful. Okay. So I wrote here the general form in terms of these 3D integrals. These integrals can be performed analytically in simplifying limits. So let me report to you the results. Is there a question? I'm just picking them out of a hat. This one, I'm imagining there's a model where dark matter is annihilating to electrons and positrons, which it does in some models. And these are just interactions present in the standard model. That this will be faster than the Hubble rate if temperature is larger than about a keV. And this, so if we this sort of goes away around an MeV. So imagine we're at temperatures above an MeV, then these will always be rapid, and then they allow me. And indeed, there are many other interactions in the standard model that will imply even more relationships. But these 3 was sufficient for me to conclude that the dark matter had no chemical potential. And if I'm just interested in the dark matter, I could stop now.
Are they consistent interaction, or they imply the same thing, or is it kind of relevant?
That it is dark matter. Sorry, it is model dependent whether or not dark matter has a chemical potential. And here I've only shown that if it's annihilating into electron positron, then it won't when these are active. And there are models in dark sectors where you say only have 2 to 2 interactions. Here, the fact you had 2 to 3 was actually important for me able to show that mu is 0. So in models where there are only 2 to 2, you can actually have a non-zero chemical potential. It can change the dark matter abundance. It's sort of interesting. That's a topic that's sort of at the edge of what people are thinking about. Okay. So I'm going to show what happens if you plug into these. In general, you can do sort of 2 of the integrals analytically, and there's 1 integral you're stuck with numerically, but then you can take special limits, and then everything is simple. And actually, this morning I already reported to you some of these results, but the number then. So let me take the limit where you're relativistic. And I'm going to use the word relativistic synonymously with saying that the temperature is much larger than the mass and chemical potential, to be careful. And then the number density, let's see. So for bosons, you have a zeta function over pi squared g t cubed. This is a boson. This thing is about 1.2. And here you get 3/4 and boson for fermion. We're often not going to need the order 1 number. One goal of these lectures is to teach you how to do back of the envelope estimates. So the useful thing to remember is just n goes as t cubed when you're relativistic. And by dimensional analysis, that's sort of the only scale. So that's sort of what you could have guessed, and then there's some order 1 number. Okay. And if you do compute the pressure in this relativistic limit, you'll find that it's energy density over 3, so the equation of state is 1/3, and that's what a relativistic gas looks like. Yes, sorry, W is P over rho. Okay. I should give you rho before I jump to P. Sorry, I want to tell you rho. This is pi squared over 30 g to the 4th, and then this is just for boson, and 7/8 rho boson for fermion. That's the famous 7/8. Okay. And again, the useful thing to remember for back of the envelope estimates is some say order one number times t to the 4th. So for relativistic gases, their number density goes as t cubed and their energy density goes as t to the 4th. So please commit those facts to memory. Okay, we're learning just dimensional analysis. Okay, now if it's non-relativistic, this is going to be very important for things like dark matter freeze out, where it's going to turn non-relativistic, and that's going to trigger a freeze out. Okay, so here, the number density, yeah, I'm sorry, so I mean temperature much less than mass. The number density will go, so it's going to be the following ugly prefactor. And then here's the important part, the exponential of minus m minus mu over t. Often we'll be interested in the case where it's just minus m over t and mu is 0. And the energy density will be just mass times number density, since energy is mass when you're non-relativistic. And in this case, if you work out the pressure, you get number density times temperature. So that equation of state, which is pressure over energy density, is going to go like T over M, which goes to 0 in the non-relativistic limit. Okay. So this exponential is going to be the important thing to remember. So just remember that when you're non-relativistic, the number density for 0 chemical potential will go like e to the minus m over t. So the three things that I want you to try to remember, yeah, are radiation, number density t cubed, energy density t to the 4th. Something non-relativistic, number density goes e to the minus m over t, which is just the Maxwell-Boltzmann distribution. Okay. Any questions so far? I'm just jumping to the answers, but the integrals are not too hard to do. Okay. Yes. Well, I didn't say where it comes from, but it comes from doing the integral and then the plus or minus 1 ends up mattering. So I'm just reporting to you the answer. I think there's slightly more details in the notes that were sent around. But, okay. We can define the total radiation density, and in the radiation dominated area, this is what's going to drive the Hubble expansion. So the total density of and you see the energy density of non-relativistic stuff is exponentially suppressed because of this exponential. So therefore, if you have both relativistic stuff and non-relativistic stuff, the relativistic stuff will dominate the energy density, because here you have this t to the 4th, and here you have this exponential. So if you so that in the radiation dominated area, you're going to be dominated by the radiation, and you can just sum up these for every state that's relativistic at any moment, and that tells you the energy density of radiation. And then, but we like this equation, so what we do, and I mentioned this, is we define a parameter G star so that we can write the total radiation density and make it look like this. You can take this actually as a definition of G star, but then G star is approximately given just by summing over all the relativistic degrees of freedom. Yeah, so we can write G star. And approximately, you can treat it as a step function where you just count things when the temperature is larger than their mass. If you want to treat the threshold case a little more carefully, there's an integral you can do that's in the notes, but let's just do the step function here. So I want to sum over relativistic bosons and then you sum each one's degree of freedom. And in general, things can have different temperatures. So I can associate a temperature with each species. In the standard model cosmology, this is important because neutrinos decouple from the photons and have slightly different temperature. Once you're dealing with dark matter, that can be a third temperature in the game. Sorry, we have a 7/8 some relativistic fermions. Okay. And here, just to be careful, when I say relativistic boson, I mean all states whose mass is less than its temperature. And same here. So the statement that I'm only including the relativistic ones in the sum is a step function treatment as temperature crosses the mass. And then again, you can treat the thresholds more carefully, but because it's an exponential, that as soon as you drop below, it quickly goes away. And you might ask, okay, so Ti is the temperature of each particle. What is this T? Well, this T is just whatever T I've chosen to put in this equation, and this equation defines G star. So you can choose arbitrarily any reference temperature. Often we would just take T to be the photon temperature, but you could also take it to be the dark matter temperature in cases where they're different. So this is just a choice that defines this function. Yes?
I don't quite understand why the number of degrees of freedom would scale with temperature.
Oh, sorry, because of this T to the 4. Yeah, so this is the total energy density of radiation. And now suppose you have two different species that have different temperatures at any fixed moment. Well, then the one that's hotter is going to gain from this T to the 4 relative to the one that's colder.
Sure.
So if you want to ask what's the total energy density of we're thinking of a system with multiple gases in the same volume that all have different temperatures in general, then you need to weigh each one by its temperature to the 4th because of this expression.
Okay, so G star is just a parameter. It's not exactly degrees of freedom.
Yeah, G star is just a parameter defined by this equation. And this equation, and that's just sort of arbitrarily chosen so that we can write the energy density in this form because we like this aesthetically.
Got it. Thank you.
But if everything has the same temperature, it's the number of degrees of freedom with a 7/8 for fermions.
Okay.
So it is useful intuitively to think of it that way. Okay, any other questions? Yeah, and then the Hubble during radiation domination. We said before from the Friedman equation in flat space. So given by this, and then we just plug this in, and we get something. So there's an ugly prefactor here. Square root G star over on Planck. This ugly prefactor is about 1.66. And again, when we do back of the envelope estimates, what you should remember is just that Hubble scales as temperature squared over on Planck. And this you could also deduce from dimensional analysis because you have a 1 over m Planck from Newton's constant in the Friedman equation, and then the other energy scale is the temperature when you're dealing with radiation and Hubble's mass dimension wise. So you could guess this. And then this is sort of the prefactor if you want to do things carefully. And this is going to be quite important because when we're dealing with thermorelic dark matter, we're going to want to ask, are things in equilibrium or out of equilibrium? And quantitatively, what that's going to mean is we're going to compare rates to Hubble. And then that depends on temperature. So this is sort of the clock. If you want to ask is something fast or slow, you're always asking relative to this. So that's going to be quite important. Okay. The final technological ingredient that I'm going to need is entropy before we can get to dark matter. And entropy is going to be very important. Basically, because it's a useful measure of volume.
In the Zoom chat, so maybe the person can speak up. Yeah, sorry, a
Audio
question.
doesn't
So,
work, then they could type their question and the moderators could read it.
Yes, so it says, is there G star dependent?
Yeah. Square root of G star here. So when I wrote that, I'm just neglecting order one numbers, but this, G star, it could be 100. So that's pretty effective. Yeah. But yeah, Hubble goes a square root of G star. Okay, so entropy is conserved in equilibrium, which is often a good approximation unless if something drastic like a phase transition happens. So if things are peaceful, then you have conservation of entropy. So consider a co-moving volume V, which again will scale as a cube. So it's constant volume and co-moving coordinates. Then the total entropy in this co-moving volume will remain constant in equilibrium. Is conserved. Volume. And therefore, we can define an entropy density which will be the total entropy per co-moving volume. And this, because now it's a density, so it has energy cubed units. And it turns out that the second law you can show implies that this can be written like this: the energy density plus the pressure over the temperature. The entropy will be dominated by the relativistic states. So then the equation of state tells you that this is just 1/3 this. So this 4/3 rho per T. That's the entropy density. And now we can, and this will be, well, this is sort of summed over all the radiation. So we can define the total entropy density of the universe summing over all the radiation that's around. And this will be given by, we just want to sum this expression for everything. And once you include this 4/3. And again, just like from before, this is really a definition of G star S, but G star S is going to count the number of degrees of freedom, yes?
Sorry, but this volume would be rather a physical volume, or am I wrong?
Sure. It goes a volume. It goes like a cubed in physical coordinates and constant volume in co-moving coordinates.
Okay, but that's.
And then I call that a co-moving volume, by which I mean
Okay,
constant. So it has, if its volume is 10 in whatever units, it stays 10 in co-moving. So I call it co-moving volume.
Would this still work if we weren't assuming homogeneity and iconosity?
Oh God, I'm assuming that everywhere,
Okay.
please. And that'll be good. That tends to be a very good assumption for dark matter production, because dark matter production happens at early times. So the perturbations that affect, say, structure growth later can be neglected. So for thermal relics, when you calculate them in a dark matter, assuming an exactly homogeneous universe is I'm not aware of any situations where that breaks down. Okay. So now G star S, which is not G star, but it's similar. And this time it's sum over boson. So it's basically the same, but now it's T cubes. Because this rho over T goes like T cubed. And then if the T's are different, then the T cube versus T to the fourth matters. So if all temperatures are equal, then G star equals G star S, and it's just the degrees of freedom. But when temperatures differ, you need to be careful, and then these become cubes, and G star S can be different. So in the standard model, they differ after neutrinos decouple, and they're the same above. Okay. And So because this thing is constant, this thing goes like a cubed. So therefore, this is a measure of a to the -3, or so really the purpose of entropy density in these dark matter calculations is often just a way of measuring volume, and it's convenient because it's expressed in terms of thermodynamic quantities like temperature. So it's like a thermodynamic way of tracking volume. And number densities dilute as universe expands. So we'll often be interested in cool moving number density. Which is also called yield. So for species I, this will be defined to be the number density of I per entropy density. This is dimensionless because both have units of energy cubed. And this is going to be what trends to a constant for a state that is inert, that's not interacting, which would be dark matter at late times. So dark matter at late times will have some constant value of Y. And that'll be sort of our target when we're aiming models at it. So this, again, because this proportional to Ni times the volume because of entropy conservation. So this is observed particle. That's going to be very useful for dark matter models, because if you want to ask what n should I calculate, then that depends on the temperature, what the n should be, because you have to track the expansion. But if you ask what y should I get, then there's just one value that you should get. So. Okay, that concludes yeah.
Sorry, so you said that entropy is conserved as long as we're in equilibrium.
Yes.
We know in the early universal processes which escape from equilibrium. So how can we know that entropy conservation is a good approximation?
Yeah, that's an excellent question, actually. And which processes do you mean?
Just for example, dark matter freeze out. Or
Yeah, good.
whatever.
That's a very good question. And indeed, yes. So the point is, for dark matter freeze out in the sort of thermal relic paradigm that I'll describe, its number density is exponentially small at the moment it freezes out, and therefore there is actually a departure from equilibrium, but the entropy produced by that is exponentially suppressed relative to the total energy around. So that's actually a really good question. It's not obvious, but it's a good approximation. So when things turn non-relativistic and then decouple, then equilibrium is actually still a good approximation.
Okay,
It's a bad approximation only if something dramatic happens relative to the total ambient energy density, like a first order phase transition. Boom, then you make a ton of entropy, these Y's will all jump down. Okay. So that's all the technology I want to introduce. And now I'm in the last few minutes today, and then tomorrow I'm going to apply this technology to consider a bunch of different dark matter scenarios. So any questions about the technology? Yeah, like a reading, say, the beginning of Colvin Turner is an excellent way of getting this in more detail than I had time for here. Yeah, so we finished these two first. So now let's talk about WIMPs. And I'm only going to talk about the production. I'm not going to talk about models. Yeah, actually, I should say in all of these lectures, I'm not going to talk about models. I might throw in a few particles, but if you ask me about naturalness or something, then I'm going to frown at you and say some other. You should really, so these lectures are in the spirit of toy models that illustrate cosmological mechanisms that are broadly applicable to many different Lagrangians. So I think there'll be another set of lectures on WIMPs in their sort of proper model framework. Okay, so for me, what I mean by a WIMP is we're going to assume dark matter begins in chemical and kinetic equilibrium. And the chemical equilibrium is ensured by some annihilations into something that I'll call phi. And people would, when they're strictly talking about WIMPs, they might mean weak interactions and that it has to be a standard model particle. I'm going to really mean a generalized notion of WIMP here. So phi could be a standard model particle. It could even be a particle beyond the standard model, like within a hidden sector. But I am going to, for now, I'm going to assume that the dark matter temperature is the photon temperature. And later in these lectures, I'm going to relax that assumption and talk about some of the cool things that can happen if the dark temperature is different. But for now, I'm going to take one common temperature, dark matter is annihilating into something, And now these will start fast, and then at some point they'll become slower in the expansion rate, and then you're done. Yep.
And are you assuming as the universe is evolving, those temperatures are tracking each other, or is it just
Yeah.
at the
Yeah, I mean-
time that we're? Yeah.
Oh, well, really, I'm only sensitive to the moment of freeze out, which I'll describe what that is in a moment. So really, I just have to make the assumption at one time. But let's just say always for
Okay.
yeah. So let's just say they track each other. Okay. And there's sort of a picture we can draw for WIMPs, which will actually apply universally to thermal relics. We're here. The y-axis will be the yield variable that I introduced. So this is the number density of the dark matter per entropy. And people often use a dimensionless measure of inverse temperature. And you can normalize to say the dark matter mass here. So now as the universe, as you go forward in the universe, x increases. So it's sort of a clock variable. And it's dimensionless inverse temperature. And then you're going to begin with this large. This is going to be number of chi will be comparable to the number of photons. And then when the temperature crosses the dark matter mass, this falls exponentially from the Boltzmann distribution that we wrote before for non-relativistic equilibrium states. So this is falling exponentially. So here, say the yield is proportional to e to the minus pi over t, or that's the same as e to the minus x. And then at some point, as the number density falls exponentially, these become so dilute that they can't find each other. I'll make that parametrically precise in a moment. But then at some point, the annihilation rate will be slower than the Hubble expansion. And then very roughly, you just become constant. And that's why the yield is a useful variable, because you're constant. If we had plotted number density, it would still be diluting just from the expansion. Yeah, so here, this say dotted line would be the equilibrium distribution. So you start along the equilibrium distribution, whose analytical form I gave you before, and then you become constant. So that's sort of a rough, sort of telling you the answer of this moment where you depart from equilibrium and become constant is called freeze out. And then the key to this game is to understand when that happens and how much dark matter there is at that moment, and then you're done. And this, when does this happen? Roughly say x of 20-ish, or maybe say if 10 to 30 in a broader set of models. So you're sort of non-relativistic, but not too much. If x were 1,000, then the exponential is 0, so you can never get to too big x. Okay.
I have a quick question on that.
Yes.
So I always see that 20 and 25 thrown around for that X freeze out.
Mhm.
Is that restricted to some coupling and mass range, or I don't know where that number comes about?
Well, if you demand that this reproduces the amount of observed dark matter,
Right.
then you can ask what x should I have. And I think I'm going to go through this later. But then because of the exponential, it's only logarithmically sensitive to the mass. If you ask what x should I have so that I have the observed number density. So it turns out that if I vary the mass from say keV to many TeV, so over 10 to the 9 or whatever, then this varies by a factor of 2 or 3.
I see.
Yes.
So when we talk about thermal freeze out, what you're really saying is that like chemical equilibrium is broken.
Exactly. Thank you.
But kinetic equilibrium might not be.
Yeah, and indeed, it's normally assumed in these models that kinetic equilibrium is maintained throughout the freeze out. If that's not true, then the calculation is much harder. So thank you for asking this. If we kind of go technically one more level deeper, here I'm assuming that I'm in kinetic equilibrium throughout this process. I start with 0 chemical potential, which is why there's no mu here. And then this moment, the chemical potential turns on that sets the yield to be constant. And this you can call chemical decoupling. So I'm in kinetic equilibrium, and then the freeze out is a departure of chemical equilibrium, exactly what you said.
We follow up on person's question. Is the mass, is the temperature also change in different models, or is it really the mass is changing and that affects the value of the x? Like, they agree on temperature, like I guess when this happened, or today, does it really depend on the mass?
It mostly x should be this value of 10 to 30. It's not for a very wide range of masses. So I can vary the mass over many orders of magnitude, and then x will always So which just tells you this freeze out event happens sort of soon after you turn non-relativistic.
Yeah, the temperature is fixed.
Well, to be at x of 10 to 30, yeah. So tell me a mass, and now I tell you the freeze out temperature given that x is 10 to 30. So you can vary the mass over many different choices. The freeze out will always happen right after you turn non-relativistic. Yeah.
I am a bit confused with the freedom that you say about varying the mass. Like there are these papers from the Ambine that are very old, that for fermionic matter below 2 GeV you cannot.
Yeah,
plan.
I'm assuming that'll appear in your WIMP lectures, but yeah, that's very model specific. That's if you're annihilating through the weak interactions, then you have a higher dimension operator
So
that
then-
dictates the annihilation, and then the annihilation rate it ends up being smaller than the size you need if the mass is too small. So it's a very specific model.
You can vary the mass, but then you also have to tune the cross section.
Yeah, exactly. So in order for this to happen at the right moment, the cross section has to have a particular size. I'm going to talk about that.
Yeah.
In a moment, Lee Weinberg is actually about the size of the cross section, even though they frame it in terms of mass. Yeah.
Is freeze out also dependent on the coupling strength?
Yeah. Yeah. So maybe it's going to depend on the cross section and therefore on the coupling, and I'm going to explain how in a moment. Okay. So I want to analyze this in two ways. First, just an approximate way, which turns out to get the answer right to within a factor of 2 and kind of captures all the intuition. So that's my preferred way of thinking. But then, well, if you want to write a paper, the referee is going to make you write a plot, have a plot with the numbers correct and stuff, and that's where you're going to need to know this. The Boltzmann equation. And if you're kind of a top-down thinker, then really this is the rigorous way of doing it, and this is an approximation to the solution of this. But I'm going to sort of explain things in the more intuitive order. But to do things carefully, you're solving a Boltzmann equation. That's what you're doing technically. The solution of that Boltzmann equation can be described within a factor of 2 using a sudden freeze-out approximation, which is very simple to frame and applies to many models, even beyond the WIMP. So it will be really useful to these lectures. Yeah.
Ask a quick question about chemical equilibrium.
Yeah.
So you said that's the chemical equilibrium until freeze-out. So chemical equilibrium is just one direction or both?
It's both. This is important. This reaction, when I say that I have this, it's really happening in both directions. So dark matter can be depleted, and then also the bath particles are making dark matter. They're both happening, and that is what allows you to maintain an equilibrium distribution. And then, so sort of they're both happening, and then neither are happening roughly.
I always thought that at this point already the phi to pi was sort of the best.
Well, it just in the sense that you follow equilibrium.
Okay.
So which goes so the number density is falling exponentially as a function of time, and that's because this is happening more than that. But you don't even need to talk about forward backward. You just need to know it's in equilibrium. I know the equation.
Okay.
Okay. So first, let's do sudden freeze out. Okay. Do I get a few extra minutes because it's technical?
You heard the poop.
Okay. I'm gonna do this very approximately. I want to teach you how to do sudden freeze out on the back of an envelope. I guess that's kind of dated on your iPhone notes app. And I'm gonna not only use God-given units, obviously, where H bar and C are 1, but I'm gonna furthermore ignore G star and ignore pi, and I'm going to ignore numbers. So this type of units I call Josh units, and it's like it's one step. Okay, so freeze out is the moment the rate of annihilations is Hubble. The rate of annihilations is the number density of chi, because you sort of one chi needs to find another one. So if you ask per chi, how rapidly does this happen? It goes with the number density times the cross section. And this notation means it's thermally averaged, which we can talk about later or offline about how to do that technically. But it's the thermally averaged cross section. It has the same dimensions as cross section. So freeze out is when this, sorry, that's an equal sign, is approximately Hubble. Really, it could be order 1 number times Hubble, so it's not any deep reason that it turns out actually just Hubble works really well. Okay, and that's it really. So you just solve that. This is the number density at freeze out. It's just Hubble over sigma. So we're done. But now let's just ask sort of how much dark matter do we need? And I kind of warned you, I like to use equality as a measure of how much dark matter there is. So let me explain what the target is. So omega chi h squared is this 0.12, but in these Josh units it's 1. So we want to get an order 1 amount of dark matter. This is going to be proportional, obviously, to the dark matter mass, and it's going to be proportional to the yield after freeze out, right? So here by y, I mean this constant value that you ended up in. And now we could just ask what's the kind of constant of proportionality here. This has mass dimension 1, so there has to be some mass to divide this by. And this is where equality is useful. So the energy density, equality is defined to be where the energy density of dark matter is equal to the energy density of photons. Okay, and now because the yield is divided by entropy, I want to rewrite things in terms of entropy. And at the sort of crude level, this is just going to be the temperature at equality times the entropy at equality. Why? Because entropy, remember, went like T cubed, and energy density went like T to the 4th. I'm neglecting the 4th Hertz factor here again. So the energy density of photons at equality is the temperature of matter radiation equality times the entropy at equality. Okay. So this is just the definition of matter radiation equality. Again, this number we observe 0.8 eV. That's all I need. So now, if we want to evaluate this, say, at the moment of freeze out, it's constant after freeze out. So omega chi. Sorry, let's step backward here. So m chi, y chi. Now, let me just to be careful. This is the condition that sets freeze out. So then I can solve for the number density at freeze out, and this would be Hubble evaluated at freeze out, right? So this is the yield at this moment. But then I can use the fact that it's constant to say that this is the same as y chi at equality, because y is constant. Yeah, sure.
In that equation, the top one, why would you have number density instead of yield? I would expect yield to be there.
Well, it's because rate, goes as density. Yeah, I mean, dimensions.
I was thinking we're setting equal to Hubble, so I would want something. I don't
Yeah,
know.
this has units of energy,
Uh-huh.
and this has units of energy because this goes energy cubed, and this goes 1 over energy squared.
Sure.
But yeah, if you ask what's the rate that one chi can annihilate with another, and then it ends up that it's the density that I see another chi times cross section.
Okay.
Because the cross section removes 2 of the units from the volume, and then you're left with just the time. So you can think of volume as area squared times time when C is 1. So.
Okay, thank you.
Okay. So this step is just because y is constant, and now I can use this to get at y chi equilibrium. Right? So this is just m chi n chi equilibrium over s chi equilibrium. That's just the definition of yield. And then and this here, the numerator is just rho chi equilibrium, right? Because rho is just mass times number density for non-relativistic thing. Okay, and now, oops, sorry, I don't know why I put chi in that. This is just entropy. Okay, and now I use this definition of equality here. So I plug in, and the S equalities cancel, and I just get temperature of matter radiation equality. So that was a long way of saying, what should the mass times the yield be? The mass times the yield should be the temperature of matter radiation equality. And that's the kind of precise way of making precise what I said earlier, that T equality measures the amount of dark matter. So if you want this model to match observation, mass times yield up to order 1 numbers is the temperature of matter radiation equality, which is the EV scale. Okay. So it's a bunch of actually very simple steps giving a deep statement. Maybe it seems a little like I played a trick on you, but I didn't. So therefore, the energy density of chi we can estimate as the m chi y chi over T equality, right? That was the dimensionless number we were missing. When I told before I argued that it was proportional to m times y, but I said what's the constant proportionality? It's 1 over temperature matter radiation equality. Okay, and now I can solve this relation for the number density and plug in here. So now we're calculating the amount of energy density produced by freeze out, and I have m chi Hubble at freeze out over entropy density at freeze out, temperature matter radiation equality, cross section. Okay. So all I did was I used that y was n over entropy, and then I solved this for n and plugged it in. So this is so this step is just the sudden freeze out approximation. Yeah.
This argument won't work if the reaction is a decay of dark matter, right? Because then you don't have any dark matter in the rate.
Yeah, you're right. This will be kind of a little clearer when I get to here. The Boltzmann equation takes a different form for decay, and then indeed this expression applies for a 2 to 2. It really just applies to dark matter annihilating another dark matter. You wouldn't want decay to be faster than Hubble because the dark matter would be too short-lived. You can consider decays into dark matter, but you probably don't want the dark matter itself decaying. Later on, when we get to non-thermal models, I'll talk about cases where something decays into dark matter, and then indeed this is not going to apply. You're right. So this is just special to this process. It does not apply to other processes. Okay. Okay, so now is the part where I'm going to really lean on these units. And I'm going to say that Hubble is about T squared over m Planck. Entropy is about T cubed. And the temperature, right, just solving this, is m over x. And I'm going to even neglect, because we're going to use now this unit, to neglect the fact that x is like 10 to 20, and I'm just going to call this like about m, because once the temperature crosses the mass, the exponential suppression turns on immediately. So within a factor of 10, who cares? Okay, so then if I plug all that in, all the t's and m's cancel, and I get something simple. T equality. And Planck sigma v. So yeah, so the reason I stripped out all the order 1 numbers is to get something very simple that emphasizes the kind of key scales involved to give you some intuition. Because a lot of references do keep all the other numbers, and then you kind of get maybe lose the intuition. So we have T equality because that measures the amount of dark matter we need. We have the Planck scale, which entered through Hubble, and then it goes as 1 over cross section. So more cross section means less dark matter. That's because if the cross section is bigger, you could fall down this exponential longer before the freeze out moment. If the cross section were smaller, you would freeze out sooner. So really the cross section is setting when this happens, and then the relative density goes as 1 over the cross section. And now I'll just finish in a second. So this, we observe this to be order 1. So that tells us, if we ask what should the annihilation rate of dark matter be to reproduce observation, then we say the cross section has to go with 1 over T equality and Planck. The geometric mean of T equality, this is around an EV, this is 10 to 19 GeV. This turns out to be about 100 TeV, which is not too far from the weak interaction. So when people say WIM miracle, this is the WIM miracle it's just this numerological statement that the geometric mean of these two very different cosmological scales turns out to be sort of near the weak scale. So does that mean anything deeper, or is it just an accident? I don't know, but it's a sort of $1 billion observation at least. And now, if you ask what should the mass of dark matter be, well, in like actual wind models that Jonathan will talk about, you'll typically get some coupling strength over mass scale. So like very roughly, you might go like alpha of the weak interactions over the dark matter mass squared. This would apply if you're like annihilating into W's and Z's. And now you just plug that into here and solve for M. You get that the mass of dark matter should be like some weak coupling times this geometric mean. And if this is say a few percent, and this is 100, then you get this sort of TeV-ish. So you sort of get TeV if you plug in a weak interaction strength here. So that was sort of advantage of dropping order one numbers was to zoom in on the important scales here. So to repeat, the energy density, so freeze out happens here. The energy density is mass times yield over T equality. This applies to any dark matter model. And then just plugging in the freeze out, neglecting order one numbers, you find that the energy density goes as 1 over T equality on plane times cross section. Therefore, to reproduce the order one number we see, the cross section should go like 1 over T equality on Planck. That turns out to be near the weak scale. So it turns out that a weak scale mass works, even though this calculation a priori knew nothing about weak interactions. It just knows about the T equality we observe, the Planck scale that enters Hubble, and it turns out weak scale works, which is really cool. Or a red herring. Okay, so I guess I'm out of time. So Boltzmann equation has to wait.
I think it has to wait. Yeah. Thank you, John.
Thank you.
Quick announcement. So the online people asked for if anyone is taking notes with their tablet and they're willing to log into